Okay, so now we're going to talk about how you deal with two dimensions at once. So something that's moving both in x and in y. And the trick is that you don't deal with two dimensions at once, you deal with them one at a time. So we're going to do a very simple problem. I'm going to kick this ball, and I'm going to kick it off a cliff, and I'm going to kick it straight off the cliff. Perfectly horizontal, because that's awesome. I wish I could do that. I actually suck at kicking things. I can't kick very hard. So let's kick this so that it leaves the cliff with a velocity of, how about 20 meters per second? I probably can't do that, but let's pretend for a moment. Okay. And I have a couple of questions I want to ask. First off, if this cliff is, say, let's make it a nice number. How about 100 meters? It's 100 meters tall. Okay. How long until it hits the ground? And how far away does it hit the ground? Okay. Well, it turns out that x and y are completely independent. They really have absolutely nothing to do with each other. So we just set them up as completely separate problems. All right. So I'm going to set up x stuff over here and y stuff on the other page. I'm leaving more room for y because that's going to have more work. It usually does, because y is the one with gravity in it, and x has no gravity. And once I'm finished kicking it, if there's no gravity, there's no acceleration. So basically what I'm looking at is, if I want to know how far it goes, that's going to be x. X is going to tell me how far this direction it goes. That's how far until it hits the ground. So I know that I'm starting at 0. I want to know how far it goes. I know its initial velocity, because its initial velocity is only in the x direction, so I know that it's 20 meters per second. I don't know, well, I will in a second, its velocity at time t. I also need a, and I need t. Now here's the thing. In that direction, nothing is touching it after I kick it. Nothing is pulling on it, nothing is pushing on it. The acceleration should be 0. Gravity does not work horizontally, so we don't care about gravity in this dimension. Well, if the acceleration is 0, then I know v is also whatever it was to start it with, so it's 20 meters per second. Basically, if I can find t, I'll be able to find this distance really easily with this equation. X naught plus v naught t plus 1/2 at squared. That's an a. Well, a is 0, so I don't even care about this. I'm counting x naught 0, so basically all I have is x equals vt. I know v, all I need is t. So, how long until it hits the ground? Well, that depends on how far it has to fall. That's where y comes in. Y. So in the y direction, I have a little more information. I'm going to, let's see, oops, sorry, that didn't work. Well, my initial position is actually 100 meters above the floor, so that's my initial position. At time t, that is until it hits the ground, this position will be 0 because it hits the ground. Yeah, that sounded stupid, I'm sorry. V naught. Now this is an interesting one. It's definitely moving at the start, but it's moving in the x direction only. When it starts off, it is not moving up and down. So the initial velocity in the y direction, I'm going to put a little y on there just to make sure we're really clear on this, is 0. I don't know what it's going to be when it hits the ground, but I do know the acceleration. The acceleration is gravity, so negative 9.8 meters per second squared. We can use 10, but I'm going to use 9.8 today because that's what WebAssign uses, and I just want us to get used to that. Okay. T. I don't know t, but it sure would be nice to know t, because then I could put it over here. So I think that's the thing I'm going to try and solve for. I don't know Vy, and I don't actually really care. So I'm going to leave that one alone. Well, I've got 1, 2, 3. I've got 4 of my 6 things, which means this is solvable. Let's see, what should I use? I want t, so I'm not going to use the last equation because that doesn't have t in it. I have acceleration and I have a distance. I think I'm going to use the big equation, the one that everyone hates because it's so long. I love this equation. V naught t plus 1. I'm having trouble writing today. I'm sorry. At squared. Now, I want t. Let's plug in some zeros first to get rid of some stuff. For instance, v naught is 0, so this is gone. Goodbye. This is 0, so I'm going to end up with 0 equals y naught plus 1/2 at squared. Okay. So if I do a bunch of algebra, move the y naught to the left side, then I'll have to get rid of the half at. I will end up with t squared equals negative y naught. Sorry, that's an old joke. Everyone does that. Sorry. Over 1/2 a. Like that. Okay. So let's plug some numbers in. I've got negative y naught, so 100 meters, and 1/2 of a is 4.9, so I'm going to have negative 4.9 since it's negative 9.8 meters per second squared. There we go. Okay. Notice the meters cancel out, and I have a fraction over fraction, so what I'm getting here are seconds squared, which is good because I've got a t squared. So if I do all that, and then t, I gotta square root it too, put that in a calculator, and I will get 4.5 seconds. So that is how long until it hits the ground. So it's going to do something like this. Blop. That's not a great picture. It should be a more parabola looking, sorry, but yeah, you get the idea. Well, if that's how long it has until it hits the ground, that's how long it has to travel in the x direction. So that is the time that we will use over here, 4.5 seconds, which means I'm ready to plug stuff into this equation. I'll just stick with this blue. Okay, so I get 20 meters per second times 4.5 seconds gives me, and that gives me 90 meters. Boom and boom. We can also at this point find things like what was its velocity when it hit the ground, and well, that's actually all we can still find, but we'll do that one at a later time.